In this session, we will cover hyphenated techniques and spectroscopic techniques. Before we go further, I must explain that all techniques like chromatographic techniques or spectroscopic techniques, they are all indicative. They are not confirmatory. Indicative because they only indicate with reference to what we carry out the experiment with. For example, based on adsorption, based on solubility, partitioning, polarity, the components separate, having equilibrium between mobile phase and stationary phase. The results only indicate that this component may be present, but it does not confirm. In order to confirm it, hyphenated techniques are the best techniques. What the technique is hyphenated with? It is nothing but mass spectrometer. Okay. Mass detector attached with the gas chromatograph or liquid chromatograph becomes GC mass or LC mass. That is the hyphenated technique. These techniques are quantitative as well as confirmatory. Identification is possible on comparison to standard mass spectrometry libraries. One can create the libraries taking the standard sample, having the complete mass spectra, create library, and unknown sample when one receives. Always go back to library and check it. The charged particle ions pass through electric and magnetic fields. Okay? Their paths vary according to their mass to charge ratio. And remember, mass to charge ratio is unique. Not each constituent will have its mass to charge ratio unique. That is why these techniques are called confirmatory techniques. On the basis of mass to charge ratio of charged particles, it is possible therefore to develop library. As I just said, if you have library, standard library, unknown compounds can be determined. This is the technique which can help us even differentiate isotopic composition of the elements. If we can even determine the structure of the organic compounds. How do we do the structure? First fragmentation will give us the mass. Those fragments we can further fragment. We can have mass, like GC mass, LC mass. When I say first mass, that means fragment, mass by charge ratio, I do it. And for each fragment, I can further, it is possible to fragment it. Further fragmentation will clarify what the structure is. So, LC mass, GC mass, and LC mass, GC mass will be the best for confirmatory and to find out the structure. What is the structure of the component? Not just the elements present, but its structure. So let us talk about gas chromatography with mass spectrometry, hyphenated GC mass. Each solute that exists from the column diverted to mass spectrometer, the MS portion of the system. Okay. Each gaseous solute eluting out of the gas chromatograph goes to the mass spectrometer detector, ionizes there, and it becomes in the form of an electron beam. The ions formed there are then directed down to a separator, okay, in the mass spectrometer detector. It isolates each component and counts the ions according to their mass. We have already said that mass by charge ratio, they are differentiated. The sequence and relative intensity of each mass peak will give the information about the chemical identity of the solute. We all already know that mass by charge ratio is unique for a given element, given component. The absolute intensity of the peak will give us the concentration, okay? Information about the amount, about the concentration. So this is about gas chromatography, mass spectrometry. Let's see liquid chromatography, mass spectrometry. Exactly the same. LCMS, as we know, different from GC in the sense that the mobile phase is liquid. Okay. So analytical technique that combines separation of LC, mobile phase is liquid, but hyphenated with mass spectrometry. In the same way, the ions would be generated here, and those ions would be analyzed, isolated based on mass by charge ratio and analyze. What are the techniques for creating the ions? Either by electron impact, we bombard the energetic electrons, or by fragmentation pattern. We can also ionize by chemical ionization, that is reagent gaseous ions or proton adducts. Okay, both the kind of techniques are, but the equipment based on both the techniques are available. Depending on what our requirement, what kind of samples we are analyzing, either we do it by EI or we do it by CI. Now, different types of mass analyzers, okay, the detectors, the analysis done by, for example, in LCMS. Either we can have single quadrupole, we can have triple quadrupole, we can have ion drop, time of the flight, and quadrupole time of flight. Clubbed together, quadrupole and time of flight. The quadrupole and ion trap instruments are highly sensitive, used for target-oriented residue analysis, whereas TOF and TOP instruments are mainly used for accurate mass analysis and structure identities, okay, because they are talking of molecular weight and non-target compounds, metabolite identifications, etc. Now look at the quadrupole. You have source, you have high charge. Remember, the ions are created under a very, very high vacuum. So the mass spectra is all operated under a high vacuum. In the case up to separation, in HPLC, for example, you require the high pressure for separating it. But when it goes to the mass, then it is high vacuum. Okay. So the material passing out of the column, when it goes there, it gets converted into non-resonant resonant ions. They are directed to become resonant ion, and then they go to the detector. And DC and AC voltage is applied there to create the ions in the quadrupole. Mass spectrometry detectors, therefore, components are ionized, okay, and pass through the mass analyzer. They have the ion current because they are electron beam that is detected. Now let's talk about spectroscopy and spectrometry. Remember, often people mention both without understanding the difference between the two. A spectroscopy actually is nothing but study of interactions between matter and light, the radiations. When radiations are falling on the material, then the interaction between light falling on the matter and the matter is a spectroscopy. Understanding that. But it does not create results. For doing the results, we need spectrometry. So spectrometry is nothing but application of spectroscopy to get results about what is the content of various components in a mixture. Spectrometry techniques are based on principles of spectroscopy. They can be either emission or absorption. We have already said that it is nothing but light reacting with the matter. So if the material is absorbing the light, then it is absorption spectrometry. If it is absorbing and after absorption it is emitting, or not absorbing, just emitting, then it is emission spectroscopy. Look at the electromagnetic spectrum. Here you see we have infrared, which will, if the infrared is falling on the material, then the molecules will vibrate. If the ultraviolet visible far infrared is falling, the molecules will rotate. But if the ultraviolet or visible light is falling, then there will be electronic transition. And we will see the color or non-color, the electronic transition. That means within the atom, the electrons will move from one orbital to another orbital. If we go further, higher energy like X-rays, then of course we can down and attack even atoms. Gamma rays can even knock off, X-rays can knock off electron out of the element. So this electron magnetic spectrum will give us an idea of spectroscopy in the sense that which light source is falling, which radiation is falling on the material, what kind of changes will happen in the material. I will repeat, if infrared radiations are there, molecules will vibrate. If UV and visible is there, the electrons in the atoms will go up. So UV visible is at the atomic level. IR is at the molecular level. X-rays are there even within the atom at the electron level. What are the techniques, spectrometric techniques? The first is UV visible, atomic absorption spectroscopy, inductively coupled plasma, Fourier transform infrared spectroscopy, and nuclear magnetic resonance spectroscopy. In UV visible, what is there is, we have a beam of light of UV source. We have seen in the electromagnetic spectrum, there are radiations of various wavelengths. In the UV visible, the wavelengths which fall in the ultraviolet region from the source, okay, that is the one which is used. So a beam of light from UV sources separate into its component wavelengths, various wavelengths, say for example, 200 nanometer to 800 nanometer. So a source will be radiating 200 nanometer to 8 or 400 nanometer to 800 or 500 to 800, depending on what kind of source we are using. So the light source will giving the beam of radiations, okay, various radiations of different wavelengths, component wavelengths by diffraction grating. So the light is coming from the source, and there is a diffraction grating which will grate it into different wavelengths. Each monochromatic beam, okay, is split into two parts, two equal intensity beams. So that means there is one beam which is coming of wavelength, say for example 490 nanometer. This beam will be split into equal intensity two beams. One beam will pass through the sample, okay, and the other beam will pass through the solvent in which sample is present. And the comparison is made to know how much is the sample containing the particular component. The law that is followed here is Lambert-Beer law. So imagine that the beam of a given intensity, a beam of a given wavelength is passing through solvent in which the material is dissolved. Then the intensity, for example, is I0. The same intensity, same wavelength beam is passing through the sample. Let us say intensity is I. Okay. So they are measured by the UV visible spectrometer. Now electronic detector, and they are compared. Now suppose there is transmittance, T will be I upon I0. What is I? That the intensity of the sample divided by intensity of the solvent. And absorbance will be, as per Lambert-Beer law, absorbance will be A is equal to log I0 by I. I0 is what? The solvent. I is what? The intensity of the sample. Assume that there is no absorption at a given wavelength. Okay. That means I is equal to I0. Whatever the solvent intensity is there, sample intensity, because there is no absorption. If there is no absorption, then T will be 1. Okay. Because absorbance is equal to log I0 by I. Okay. And T is equal to I by I0. If both are same, then T is equal to 1. And A will be 0 because there is no absorption at all. But if it absorbs, then the intensity of sample will be less than the intensity of the solvent. Obviously, because some light is absorbed, some UV light is absorbed by the sample. The most UV visible spectrophotometers will have on the vertical axis the range from 0 to 2, okay, for absorbance. If you are checking the absorbance, the minimum range is 0, maximum is 2. At minimum 0 means transmittance is 100%, and at 2 absorption, the transmittance is 1%. We always check the wavelength of maximum absorbance. At which wavelength, okay, the maximum absorption is there, lambda max, and this is characteristic. All compounds, visible or non-visible, okay, visible are colored, non-visible are not colored, the Y max is characteristic of the compound. The range is for the UV, it is 200 to 400 nanometer. For the visible, it is 400 to 800 nanometer. The solvents in UV visible spectrophotometer is water and ethanol, or in the organic side, hexane and cyclohexane. And the samples that you analyze, they must be completely clear. There should not be any haziness, there should not be any suspended matter. Atomic absorption spectrometry is the one where you are doing the elemental analysis, a very popular technique for assessing metals, okay, in minerals and all sorts of residue metals in food, all sorts of mineral nutrients in food, we do it by atomic absorption spectrometry. It is possible to analyze all elements present in the periodic table. It is very rapid, it is sensitive, selected for all elements, and it consists of what? First, the light source. We are doing spectrometry, so light source has to be there. In this case, the light source is cathode lamp. In fact, the hollow cathode lamp. Okay. Why cathode lamp? Because the cathode lamp supplies the radiations of the same element which we are analyzing. As a basic principle, the metal will absorb the light, same wavelength light which it emits. Okay. So, the hollow cathode lamp, which is emitting the light of a given wavelength, will be the one which will be absorbed by that metal. So, for analysis of any metal, we have to choose the hollow cathode lamp of the same metal. If we are doing the iron in food product, in water, then the lamp should also be of iron. The light source should also be of iron. If zinc, then zinc. So, the emitted light energy, emitted light which is coming from the cathode lamp will be absorbed by the sample of that metal. A sample cell, which is absorption cell, a monochromator, which will actually take care of the lights of one wavelength, detector, output unit. What is the principle of AS? We first wet digest. During the ashing, we always digest with acids, okay? And the ashing with, we say acid insoluble ash or acid soluble ash. What we do basically is we digest the material with acids, okay? And so all the elements will get into the solution. That solution is aspirated through a nebulizer into the high temperature flame. All ions present in the solution will get into their gaseous form, gaseous atoms, and those gaseous atoms are ready for absorbing the light which is coming from cathode lamp. I already told you the cathode lamp has the same metal which is targeted metal we are analyzing. So it is coming from the cathode lamp of unique wavelength, same wavelength which the metal is being tested. Electrons in the atoms move from ground state to the excited state, and the light absorbed in this process of ground state to excited state is measured, and that is used for knowing the concentration. So, light absorbed is from emission lines produced by hollow cathode lamp. The hollow cathode lamp emission lines are same which the metal we are examining. Monochromator, which is there after the material passes through the flame, monochromator isolates the specific spectrum line emitted by source through spectral dispersion and focuses upon a photomultiplier detector, which converts light signal into electrical signal, and we get the data for each element. The greater the amount of gaseous atoms present in the flame, better would be the sensitivity of the equipment, the better would be the factor for going as low as possible. Because more the gaseous atoms, more the energy absorbed, and better will be the signal. So, using the mixture of gases, we can change the temperature. Say, for example, the general temperature is about 2700 degrees centigrade of the flame. But by changing the gases, we can increase, okay? So, what do we do is some elements get to gaseous atoms only at high temperatures, okay? But to reach that temperature, suppose we use oxygen, then some metals may get oxidized to oxides. If they become oxides, then they do not redissociate into atoms. So, in order to inhibit this, the flame must be modified to achieve a reducing, non-oxidizing flame. Generally, it is preferred to have non-oxidizing flame. So, in those cases, air acetylene and nitrous oxide acetylene flames are the most widely used. I repeat, when we have the flame which is by burning the gases, because the oxygen is there, it is possible that the metals will turn into metal oxides. If they turn into metal oxides, they will not be in the gaseous atom form. Then they will not be able to absorb the light coming from the hollow cathode lamp. So in those cases, the flames are not of one gas. It is always with the reducing gas. And what is the reducing gas? Acetylene gas. So we have a mixture, air acetylene burning, nitrous oxide acetylene burning. And increase of, for example, increase of nitrous oxide, you can achieve higher temperature. A nitrous oxide acetylene flame has a higher temperature as compared to air acetylene flame. This is the picture which shows hollow cathode lamp. The emitted rays are coming, falling on the flame in which the sample is injected, and the beam is going straight to the monochromator, and monochromator is sending it to the detector, photomultiplier, which gives the record at the electronic readout. So, in certain metals like silver, beryllium, calcium, iron, lead and tin, okay, we need to have high temperature for getting the gaseous atoms. So, for that what is generally done is the graphite furnace is used. It's basically a graphite tube which provides a small contained area for atomization. And atomization is done by electrothermal heating. It's not done by the gas heating, okay. It's not the air, it is not different gases burning, it is electrothermal heating. The high temperature capabilities and containment of the sample is so high, okay, it allows the complete atomization. And the tube, the graphite tube has open ends so that the beam can pass, okay. So this graphite furnace allows the atomic absorption spectrometer to achieve very low quantification, level of quantification, LOQ is very, very low. Similarly, there is a generation of hydrides, okay. For certain elements, it may be necessary. I mean, they are, for example, lead, for example, mercury, they are supposed to be formed. They cannot be analyzed by either electrothermal, okay, or by the high temperature gas. They are supposed to be done by formation in hydrides. So what do we do here is acidified sample solution is added to a solution of sodium borohydride, okay, in a specially designed reaction cell. So all of them are converted into hydrides. The resultant volatile hydride gas is then passed on to optical cell, and the all further principle is same. Basically, the elements which are volatile, which get escaped in flame or cannot be done by graphite are done by vapor generation ASVGA, which is by formation first the hydride and hydride then to gaseous atoms. Gaseous atom then absorbs the emitted rays and we get the analysis. After the atomic absorption spectroscopy, where the temperature is 2700 degree or 3000 maximum, we have other technique, that is inductively coupled plasma. Here there is no gas, okay. So this is for analysis of trace metals, because the ICP generally has much lower LOQ, limit of quantification, than the atomic absorption spectrometer. Elements emit radiations of characteristic wavelength after they are actually subjected to plasma of the inductively coupled plasma. An aqueous solution is preferred over the organic solution, okay, and avoids solid samples because they can clog the instrument. Nebulizer transforms the aqueous solution into an aerosol. So the sample is converted into aerosol by a very high pressure, okay, jet nebulizer. The emissions are converted to electrical signal. They measure the signal quantitatively. I repeat, inductively coupled plasma is nothing but, the principle is almost similar to atomic absorption spectrometry. The only difference is no flame, okay, here it is plasma, okay. The aqueous solution, the element emit radiations after they are in the plasma. So sample injected goes to plasma arc, there it starts radiating the light, and that is what is observed to get the concentration. ICP OES involves, this is emission spectroscopy, okay. In the case of AS, that was absorption spectroscopy. Here it is emission spectroscopy. I once again repeat, for analysis of trace metals in food samples, elements which are there in the plasma due to high temperature, more than 5000 degrees centigrade, can go up to 10,000. Elements emit radiations of characteristic wavelength. So when an aqueous solution goes to plasma, the elements emit radiations of characteristic wavelength. Okay, the emissions are converted into electrical signal, and that electrical signal is measured for quantitative analysis. The ICP OES involves sample introduction system. Okay, nebulizer. It has to be very high pressure nebulizer. Okay, like small droplets. ICP torch, which is the plasma. High frequency generator, transfer optics and spectrometer and computer interface. Temperature is generally more than 5000 degrees. Okay. Wavelength of light, it is used to separate element specific wavelengths of light and to focus the resolved light onto the detector as efficiently as possible. So when the light exists, the mono or polychromator, okay, it is focused onto the detector, and the derived signal are processed to quantify this. In the case of atomic emission technique, which is ICP, argon plasma, okay, is the one which is used as an excitation source. Sample atoms experience full energy of the plasma source. The high temperature provides excellent sensitivities, especially for refractive elements which require very high temperatures, which cannot be done by AS. And by monitoring several wavelengths, either all at once or in program sequence, many elements can be detected by one automated analysis in much better way than AAS. Let's talk about other spectroscopic technique, that is FTIR. We have already talked about what infrared does. It vibrates the molecules. So infrared spectroscopy basically is for the radiations which are from 400 centimeter inverse to 4000 centimeter inverse. It is vibration, stretching and bending. So various functional groups will have characteristic frequency at which they will vibrate. So in the IR spectra, we will have several peaks based on which we will find out whether the group aldehyde is present or ketone is present, whether amine is present, which functional group is present. So the IR spectra is from 400 centimeter inverse to 4000. On the higher side is stretching, on the lower side is bending, because the vibration can be stretching and bending. Each peak in TR spectrum corresponds to stretching and bending groups. IR spectrum consists of bands, for example, proteins, carbohydrates, lipids, they all can be characterized by FTIR. It evaluates the data using multivariate statistical analysis. That's why it becomes FTIR. So it is used for characterization of essential oils in various spices, evaluation of trans fats in oils and fats. So it's a very useful technique. Let us talk about the technique thermogravimetry. As the name suggests, thermo and gravimetry. What do we do here is we measure the weight of the food sample which is being heated at a constant rate, given rate, okay, and with time we measure the weight. So we plot with temperature the loss in weight, that is thermogravimetry. To say it, continuously measure the mass of a sample, okay, when it is heated or it is cooled. Suppose there is a hot mass and we are cooling, then also thermogravimetry is done, okay, at a control rate, or it is held at a constant temperature, okay. We take a particular temperature and we just note down the loss in weight for a period of time with reference to a control sample, okay. So useful to monitor process that involves a change in mass. So when we are giving heat to the food, how the mass is changing? What are the process? The drying, liberation of gases, absorption of moisture, all this will be checked by thermogravimetry. When we are designing processes for processing of foods, thermogravimetry is very, very important for all components that are going to be used for food processing. To study various types of processing storage conditions, how the material, how the food will behave under different storage conditions, under different processing conditions. TGA or thermogravimetry is very useful. It is possible to do it under controlled pressure and controlled temperature. We can carry out thermogravimetry in nitrogen atmosphere. We can carry out thermogravimetry under pressure or under vacuum. All that is possible. The ability to carefully control the temperature, pressure and composition is there in all the equipment, that is the thermogravimetry equipment. Then there is another equipment, that is differential thermal analyzer. This also is the changes in food when we are heating it. How it is different from thermogravimetry? Here we are not checking the weight loss. In thermogravimetry, we were checking the weight changes. Here we are talking about the temperature changes when we are heating it. How it is done? We have two cells. In one cell, we take the sample. In the other cell, we take the reference material. Say for example, alumina. So we are, in both the cells, there is thermocouple. Okay. Both the cells are heated. Okay. At the control rate. And the small difference in temperature between sample cell and reference cell is delta T. And that is what is recorded. Okay. So basically, we have one cell with the sample, the other cell with the reference material. The reference material will have no change when we are heating it. The sample cell, because sample is there, it will change. The reference material is the one which will show no change throughout when it is heated up to 1000 degrees, like alumina. The sample cell there will be a lot of changes, either endothermic or exothermic reactions with the heat absorbed. But we are checking the temperature difference because both the cells are fitted with thermocouple. The output is nothing but plot of delta T versus T, okay, which is we are heating. The temperature which is raised versus the delta T at each temperature. Okay, the area under the peak will tell us about the amount of material which was involved in the transition. And the peak, the transition, the point at which it is happening, if it is on the negative side, it is endothermic. If it is on the upper side, the positive side of the graph, it is exothermic. There is another technique, that is differential scanning calorimeter. In the DTA, we had two cells and we were checking the temperature difference. Here we are checking how much electric supply we have to give to the cells to make sure that the temperature remains same. So this technique records the energy, electric energy that is supplied, required to keep the temperature difference 0. In DSC, the delta T is 0 between the reference and the sample. And how much energy is supplied to ensure this is 0? DSC. So the DSC graph will have the scanning calorimeter graph will give us the endotherm and exotherm. Basically, no temperature difference between the two. But the difference will be energy supplied. The sample has to be supplied with the energy. If it is supplied, energy is supplied to the sample, then it is endothermic reaction. Okay, enthalpy is negative. If it is withdrawing the energy when you are heating it, then it is exothermic. So we'll be able to find out. This is more for the phase changes. This is more for substances like solid liquid ratio in fat and oils. So DSC is very, very useful when it comes to energy involved in the thermal treatment of foods. We have covered chromatography, we have covered application of chromatography, we have covered various aspects of spectroscopy, we have covered various aspects of gravimetry, thermal gravimetry, DSC, DTA. I hope you enjoyed the session. Thank you very much.